So let's take a look at phase changes. And what we just saw with those equations, we can get a little more specific with phase changes. So remember, for a spontaneous process, the entropy of the universe is positive. Okay, but negative if it's not spontaneous. And if delta S is 0 for the universe, then we have an equilibrium. Okay, so this is our equation that we're using, and delta S for the system, delta S for the surroundings, and those add up to delta S for the universe. So let's consider water melting. So the system is the water. So it becomes more disordered, and energy is dispersed. So what does that mean then? Delta S for the system is going to be positive, more disorder in the liquid than in the solid. So I have a typo here. This is wrong here. Let's ignore this down here. Just ignore this. I had a typo in there and I meant to change that and I forgot. So just ignore that for right now. I apologize. So delta S for the system, if melting occurs, it's going to be positive because we're getting more disorder, more dispersal of energy. And that is not temperature dependent. Not. What we're really looking at is particles locked up in a solid becoming free to move about in a liquid. That is a big change, and whether it occurs at one temperature or another, it's not going to make too much of a difference compared to the significant change of going from a solid to a liquid. So delta S for the system is going to be positive and it's not temperature dependent. Now consider the surroundings for a second. If we have melting, heat from surroundings enters the solid in order to cause the melting to occur. So this is an endothermic process for the system, exo for the surroundings. So what do we see here? We have order increases, so delta S for the surroundings will be negative. Increasing disorder is positive delta S. So this is endothermic, so delta S will be negative. But this is going to be temperature dependent, right? Remember, if you change the temperature of the surroundings, how much it causes a change in entropy will be dependent on the temperature. If the surroundings are high temperature, that lost amount of heat will have less of an effect on the entropy of the surroundings than it would if the surroundings had a lower temperature. That loss of heat will have a more significant, profound impact on the entropy of the surroundings. So this page, I'm just summarizing here. Delta S of the system will be positive. Delta S of the surroundings will be negative. But this one is temperature dependent because of this equation. So let's just look at the summary of this. Okay. Notice that this is not changing. Okay. Below the freezing point, you don't expect melting to occur if it's colder. The temperature is below the freezing point. At the freezing point, we have an equilibrium, and above the freezing point, that's when you expect melting to be occurring. So delta S for the system is the same at any temperature because it's really all about the phase change, solid to liquid. But delta S for the surroundings, look at that. At a low temperature, Q over T is larger. But at a high temperature, Q over T is smaller. I should say the magnitude. Now notice that the delta S is negative because as the heat flows out of the system and out of the surroundings into the system, the surroundings become more orderly. So delta S is negative, but the magnitude decreases with temperature. So at a lower temperature below the freezing point, the delta S of the surroundings being negative is actually more significant. And so melting is non-spontaneous. Above the freezing point, melting is spontaneous because, yes, delta S of the surroundings is negative, but its impact is less at the higher temperature. And so the net delta S for the universe is positive, which makes it spontaneous. And then you have the special at equilibrium case where you're at the freezing point and the magnitude of the delta S for the surroundings and the system are equal. Okay, so delta S for the universe is 0. Now, just a little bit more with this particular phase change, and then we can make a more general statement about any phase change. We can talk about another relationship. At the freezing point, we have an equilibrium and delta S for the universe is 0. So if we plug that in, 0 for delta S for the universe, we can actually come to this. At equilibrium, delta S for the system is equal but opposite of the surroundings. Now, remember this equation, delta S for the surroundings is negative delta H system over T, and that's true at constant pressure because Q equals delta H under constant pressure. And also in that relationship, we had Q of the surroundings is minus Q of the system. So that's how we got to that point. So what I'm going to do is take this quantity, plug it in for delta S for the surroundings. And so I end up with this equation, delta S of the system, the negatives canceled. There was a negative here, and when I plugged in what delta S is for the surroundings, I get negative, a second negative, so it becomes positive. So delta S for the system is delta H for the system over T. And this is constant pressure at equilibrium. So this is just in general constant pressure conditions at equilibrium. And now we really want to think about this as a phase change, so we get a little more specific. It doesn't have to be a phase change, but this is usually where it comes up. So for fusion, for melting, delta H for the system is delta H fusion. So just plug that in there. So this, again, constant P at melting point. And then for any phase change, delta S for that phase change is delta H over T. Again, constant P at equilibrium. I'll just say at equilibrium. When is it at equilibrium? At the temperature that phase change occurs. So for boiling, it'd be the boiling point. Okay, and then finally, let's look at some graphs here. We've looked at these Boltzmann distributions already, and we see that the entropy is going to be higher at the higher temperature, more dispersion of energy. And so you might remember, let me just scroll down here. You might remember these curves, like heating and cooling curves. So this could be heat added. And this would be temperature going up. So you have, this is the solid. This is the liquid. From here, you have the gas, right? So we have solid. That way. So here you have melting, and here you have boiling. If you're going from left to right. So that kind of looks like this graph here, except we're not measuring the heat. I mean, you're obviously adding heat, but the measured temperature as you add heat, we're looking at the entropy. And so this part here is temperature change in the solid. And the entropy, you'll notice, look at the way that curve, sometimes you see these in books and they're not as careful. That curve, it's a curve, it's not a line, right? Look at when you increase the temperature at low temperatures, it's a greater increase in entropy. When you get to higher temperatures, it starts to level off because raising the temperature, adding heat to raise the temperature from one temperature to the next, an incrementally small, because it's Q over T, so it's supposed to be constant temperature. But if you were to think of like incrementally small changes, the entropy change due to the addition of heat is more significant at lower temperatures. So that has a bit of a curve to it. And then we have the phase change. And remember what I said before, the phase change, the entropy change is all about the phase change itself. It's really not temperature dependent because it takes place at one temperature. If you're in equilibrium, you're at one temperature. There's no temperature change during the phase change. And also, the big change in entropy is about the reorganization of the matter. Any subtle temperature change you might have, if it were to occur, if you weren't in a equilibrium situation, it would be minuscule compared to the reorganization of the matter. So we have a significant jump due to the phase change. And then you see the liquid phase, increasing temperature, increasing entropy, but then a huge jump for vaporization. Because now we lose all intermolecular forces, truly independent particles, much more dispersion of energy in the gas than the condensed phases. So that's that graph there.